Welcome to the second video on chapter 14 on chi-square tests. This video goes into the chi-square tests for independence and homogeneity. An example of when this is used is usually when you have some categorical data that you're trying to figure out if, again, it matches a certain distribution, or if your hypothesis is everything should be equal, that's still a distribution. An example could be if a researcher wanted to know if background music in a restaurant changed the purchasing behavior of the people dining out. And so an experiment was run where Italian music was played, French music was played, and I think just American music was played. And then what kind of wines did they buy, French, Italian, or American wines? And then the numbers were measured to see if it was equal, if the distribution was equal to just it not mattering what music was played. All right, so I did mention at the beginning there are two types of chi-square tests for this section: homogeneity and independence. Now the mechanics and almost everything is the same for both tests. It really just goes into how the data was collected as to what you name it. And so there has been some discussion in AP grading. Like one year, they didn't, if you didn't name it, you didn't, like if you just called it chi-square tests without naming it homogeneity or independence, you got full credit, but if you named it incorrectly, you got it wrong. And then another year, if you didn't name it, uh, you didn't get full credit either because they wanted you to name it homogeneity or independence. So I can't guarantee that if you had this question and you didn't choose homogeneity or independence as your naming convention, that you would get full credit. So it's not very hard to distinguish between the two. It's just taking the time to remember which is which. All right, so here, the distinction is in how the data is created. So there's a lot of words here, so if you want to read them, you can pause, but I'll try to explain it. Homogeneity is when you split the population into two. Well, you split your subjects into two populations. So like, let's say, do the classic males and females. And then you do your experiment or your sampling on those two blocked or stratified groups. So homogeneity is you're looking at one change, but you have two populations that you're using. Independence is you did an experiment or a study in one population, but then once you get the data, you separate the data out into two different groups. So that's independence. That's how you can tell the difference. So what homogeneity is looking for is if some variable is the same within two populations, and independence is seeing if two variables are different in one population. All right. So take a second, pause, read these, and then see if you think they're homogeneity or independence. So pause, because I'm going to give you the answer in a second. All right, here is the answer. So the first one is independence, because you're just doing the sampling on the 200 people, and then afterwards you split it up. And then the second one is homogeneity because you split it up first. All right. So doesn't matter how you do the test. I mean, it matters for your experiment or your observational study, but it doesn't matter for the rest of this video. The rest of the video, whichever one it is, you do the exact same thing. All right. So the conditions for a chi-square test for independence or homogeneity, no more than 20% of the expected counts can be less than 5 again, and all expected counts have to be greater than 1. And if you notice here again, it is expected counts, the observed counts. It's fine if you have a 0 somewhere in an observed count, that can happen, but your expected counts have to be 1 or more. Because if it was 0, why do you even have it in your distribution? You can just take it out. All right, so This is an example where we have two different populations. So we're doing homogeneity because it's broken up into two different populations, and we want to see if the distribution is the same within those two populations. And what we are measuring is the day of the week that babies are born. So before 1980, there weren't really much selective C-sections. And then that became more of a common practice after 1993, it looks like. So then if you're selecting to have a C-section, you could maybe choose the day of the week you want to have your baby. So we want to see, has it significantly changed the day of the week babies are born by that occurring more? Now, the next two pictures, you don't have to do in a hypothesis test. It's just always good practice to look at your data. So if you looked just at the data, it really looks like the after 1993, this Thursday definitely spikes up a lot, but not sure if that's enough for it to be statistically significant. But if we do get a chi-square uh, that gives us a rejection of the null, we probably want to come back and definitely look at what's going on Thursday from 7 to 17. All right. So first thing is to state your hypothesis. I would definitely uh, do this one in words. So for homogeneity, where you just have to say there's no difference in the distribution of birthdays between the people in 1980 and born before 1980 and those born after 1993. And there, the alternative is just there is a difference. So you just have to make sure you know the null is no difference, because that would be the same as like when we do a difference of means and we're just saying that the two populations, equal each other, so there's no difference in them. And the alternative is there is a difference, which would be like saying a not equals to. All right. So how do you calculate expected values? The formula is row times column, oops, all over total. So for example, to get the expected value for the Sunday here, let's go with this one. You take the row that's in total, which is 21, and times it by the column that point is in, which is 77, and then divide by the total, and that gives you the 10.78. Then if I wanted to do the after 1993, I would take the same row, multiply by the column, and then divide by the total. Now the good news is the calculator does this for you. So you usually just have to jot them down from your calculator, but if you had to calculate it, it's row times column over total. And then for degrees of freedom, you're going to do row minus 1 times column minus 1. So in this case, we have seven rows, 2 columns, so it is 1 times 6 or 6. All right. And if you had to show work for this, what is written that I'm circling is good enough work. You don't have to show all the terms, as long as you show like a couple, like 3 is good, like I have here. You can show the work. Right. And then your calculator would give you your degrees of your p-value for you, and this is not less than any alpha value we use, so we would fail to reject the null that the day of the week has changed after more elective C sections. So here would be the appropriate conclusion. We don't have convincing evidence that there is a difference in distribution of birthdays for people born before and after. All right, let me show you the calculator portion of this now, and I will go back to this in case you need to pause to put these numbers in. All right, so we're going to be putting these in matrices now. So this is the difference that you might not remember or even know. So to get to matrices, you go second matrix. Now, what I always try to do is press enter right away, which is not what you want to do, because this will just give you the matrix on the home screen. We want to edit the matrix. So you go to edit A, and you just type in the numbers for the dimensions. So I want a 7x2. And then you can go in and type in these numbers. Just know when you type them in, if you press enter, it goes to the one on the right. So it's not like you're going down a column. And then once you get them all done, you can press quit or go to your next button. I do want to show you the expected. Oops, I did it again. See, I told you I do it. You go to edit. If you look at the expected, right now it's zeros, but I'm not going to put anything in there because the calculator is going to do it for me. All right, so we're going to go to stat tests, and it is down at C for me. So chi-squared, just test, no goodness of fit. All right, so our observed we put into A. Expected, that's not where we put in the expected values. That's where we're going to tell the calculator to put the expected values. And then we just do calculate. And we got our chi-square value and our p-value and our degrees of freedom. In case you think you messed it up, you can always check it here. Now for work on a test, you would have to show your chi-squared expected values. So if you needed to get those, you can just go to the matrix. And here's where you stay on the screen and you want B. And you press enter after the matrix shows up, and you will get all your expected values in there. All right. So that was a homogeneity. Independence will be the exact same thing. It's just how the test is done. Everything else is pretty much the same. I'll show you the wording that's a little bit different, but first let me just show you the computer output. So there, if you get a computer output for chi-squared, it's generally set up the same, but you'll see it says in words where the expected counts are listed. The other way to know is the expected counts are usually the decimal ones, and the observed are always going to be integers. And so you have your observed, expected, and then you have your chi-square calculation here that gives you your p-value. So it's pretty easy to read. This one over here on top gives you your observed, whoops, your observed, expected, and then this is your chi-square contribution is right there. So how much it contributed to the total chi-square value of 8.006 is at the bottom. And if you wanted to double check that that number is correct, you can just do out one of them and see, but it does also tell you in words that it's printed below the expected value. All right, let me show you one last thing, which is the wording. Here you go. For homogeneity versus independence. Okay. So null and alternative wording. So for homogeneity, we already went over that. That's the null is there's no difference, and the alternative, there is a difference. Independence, you're going to use the wording there is no association between the two variables, and there is an association between the two variables, or 3 or 27. All right, so that is the last chi-square section. And we have one more section in the whole book, and then we are done for AP statistics.